To avoid depending on wearable trackers or external third-person cameras, we introduce EgoPoseVR, a new system that uses spatiotemporal multi-modal reasoning to capture full-body pose directly with a commercial VR headset. There are three common approaches to egocentric pose estimation. First, HMD-only tracking is simple but can't capture lower body motion and relies on sparse head and hand signals. Second, head-mounted cameras capture more body cues, but often struggle with upper body accuracy and depend on pelvis camera alignment, which fails when the pelvis moves out of view. Third, combining headsets with wearable sensors adds motion signals, but makes the system bulky, calibration heavy, and prone to drift. Our goal is accurate, real-time full-body pose estimation in VR, without body-worn sensors or external tracking. There are 5 main challenges when combining egocentric vision with VR. First, they predict only joint positions, not rotations, limiting 3D avatar control. Second, commercial headsets lack downward-facing camera access, so real VR testing is rare. Third, frame-by-frame estimation causes unstable motion with occlusion or blur. Fourth, synchronized HMD RGB-D datasets are missing. And fifth, latency still hinders real-time use. Before introducing our work, we first solved hardware and data needs. On the hardware side, we used the MetaQuest 3S with a lightweight Intel RealSense camera, linked by our custom SDK and aligned to the headset through hand-eye calibration. On the data side, we built the first synthetic dataset combining temporally aligned HMD motion and RGB-D frames across a wide range of VR scenarios. Our dataset includes over 2,300 motion sequences from the AMS dataset simulated across 8 Unreal Engine environments with HDR backgrounds. To add visual diversity, we introduced 100 garments and 20 pairs of shoes, resulting in more than 18,000 sequences and about 1.8 million frames at 60 frames per second. Each frame comes with egocentric RGB-D images, headset and controller tracking, SMPL-based 2D and 3D joints, and full camera parameters, so researchers can easily adapt it to their own models and camera setups. Our workflow follows a dual-stream spatiotemporal design. The first stream, the HMD modality module, captures motion cues from the headset and controllers. The second stream, the RGB-D modality module, extracts egocentric visual features from a downward-facing camera. We then combine these complementary signals in the cross-modal fusion module to resolve ambiguities and improve pose accuracy. Finally, the kinematic pose optimizer applies constraints guided by the raw HMD signals, resulting in natural and accurate full-body motion. To validate our approach, we compared it against representative baselines. We did not include EgoPoseVR alone, since it predicts only joint positions without rotations and depends on information not directly accessible in real VR. As the results show, EgoPoseVR mainly infers lower body motion from arm-leg coordination, which breaks down when arm swings are subtle. EgoPoseVR depend heavily on pelvis localization, so large head movements often introduce errors. By contrast, our RGB module directly leverages visible joints. With the addition of depth input and kinematic optimization, the complete EgoPoseVR system achieves more accurate and stable full-body poses. To see how each input and module contributes, we ran an ablation study. We start with a baseline that only uses HMD pose. Then we add single-frame RGB. This improves lower body accuracy, but the results are still unstable. Next, we switch to multi-frame RGB. This helps the model capture short-term continuity and produce smoother predictions. Adding depth further enhances 3D reasoning, helping resolve occlusion and motion blur. And finally, our kinematic pose optimizer brings in head and hand constraints from the HMD, refining upper body motion and giving us the most accurate full-body poses overall. Accurate 2D heat maps are essential for 3D pose estimation. Without our visibility factor zeta, out-of-view joints cause noisy responses. Adding zeta removes these artifacts and sharpens valid joints. Looking across rows with both depth and zeta, the reprojected joints align well with the image. We also tested our system in the real world. To make the comparison clear, we show avatars from different methods side by side as the user performs the same motion. As you can see, EgoPoseVR almost fails to capture lower body movement. The middle avatar shows only small leg motions, while our method closely follows the complex full body movements. Due to Wi-Fi streaming and running 3 models in parallel, the motions on the background screen appear slightly delayed. For more details, please see our paper. Thank you for watching.